this is voltage or current. I can take any signal with plus minus like that, it is continuing. Now when I give positive half cycle, then I'll represent like this, minus plus. Okay, so diode is on. So if diode is on, then we can replace with short circuit and current will flow. So I'll get here voltage as VL. So load voltage I'll get. So if I represent that one here, so this is your V out or VL, load voltage or output voltage. So we'll get same as input voltage. If I consider there is no drop across the diode, ideal diode if I consider, then if I give it here VM, then I'll get here also VM. There is no drop across the diode. Okay, is it clear?
Yes, sir.
Now if you give negative half cycle, then it will be reverse. This is plus, this is minus, this is plus, this is minus. So minus terminal is connected to positive P side and plus terminal is connected to N side, so it will be open circuit. So open circuit means current is 0, no current will flow. So VL here I'll get 0, no current, no voltage I'll get. So from here to here I'm getting 0 voltage. Again it is a repeating process, so I'll get again positive half cycle, then again 0, so it will continue. So in that process what happened, I'm getting positive half cycle and negative half cycle is clip or cut. So this alternating nature is now converted to direct current or direct signal. Though it is not perfect, because perfect means it is constant throughout the time, it is somewhat unidirectional. Okay, so that thing we have discussed. So for positive half cycle, the diode is forward biased and hence it conducts, so we'll get voltage. For negative half cycle, diode is reverse biased, so it will not conduct, so current 0, voltage 0. So the output of half-wave rectifier is pulsating in nature. Why pulsating? Because you can see one pulse, then 0, then again pulse, then 0, again pulse. So this nature is called as pulsating in nature. And if you consider the time period, then this is one time period T. So output also will get from here to here, it is repeating. So same time period. So same time period means frequency also same. So output frequency is equals to input frequency. Though in DC, do you know what is the frequency of DC signal? What is the time period of DC signal? DC means,
sir, is it infinity?
yes. See, this is my DC. Suppose 5 volt. Then what is the time period? I cannot conclude here because it is not a periodic signal. So it is continuously increasing. So T is infinite. So F equals to 0. So for perfect DC, time period is infinite and frequency is 0. We are saying it is converting AC to DC, but it is pulsating in nature. That's why we have some frequency. So that frequency is same as input frequency. Right. Now once we understand that, then we will discuss about different parameter of rectifier. So parameter means what? One very important parameter is efficiency. Okay, efficiency, and another one is the ripple factor, and another one is PIV. So efficiency means what? Do you know what is efficiency of any circuit? The general idea of efficiency, because in plus 2 level you have find efficiency of any problem, maybe somewhere
Yes, sir.
What is the general meaning of efficiency? How you find efficiency?
With the amount of output, sir.
Divided by
Amount of output.
Yes, sir.
and generally it is expressed in terms of percentage. So output by input into 100.
100.
So we can convert like 90% or 80% efficiency or 70% efficiency like that. Okay. So here also we'll see efficiency of this half-wave rectifier circuit. That means how much efficiently this AC is converted to DC can be calculated by this efficiency, and it is represented as eta. So if you see this waveform, you see the input signal is varying like this. So it is continuously AC signal. So they have some energy. So when it is converted to DC, how much efficiently it is converting this AC power to DC power. If we observe as a layman point of view, you can see the half of the power is reduced. That means you see this negative half cycle we are cutting, only we are getting the positive half cycle. So efficiency may be somewhat around 50%. Okay, it is not exact, roughly from the figure we can observe. Now mathematically we will find what is the ideal efficiency of this rectifier circuit. This is the first parameter. Second parameter is ripple factor. You do know what is ripple? Ripple means what? You have not heard the term ripple?
Yes, sir. Heard, sir. Sir, ripple means
Yes.
opposite of attraction.
To tell me the general meaning. You don't.
Sir, waves.
Yes, wave-like thing. Okay.
Yes, sir. Okay.
Ripple means wave-like thing. So when you go to seashore, you see the waves, or you can say ripple of the wave. So here, if you relate that thing to circuit point of view, then how can we relate? You see, when we take any DC, how we represent? This is my pure DC. Suppose voltage 5 volt. This is time. So constant. Here it is 5 volt DC. Now, in this case, just now we have observed what we are getting. It is not this type of waveform. We are getting this type of waveform. Right? So this is a train of pulse, or you can say this is wave-like thing. Yes or no?
Yes, sir.
Actually, these are called as pulsating DC. DC, but it is not pure DC. This is called as pulsating DC, and these are called as pure DC. So what is the difference between this pure DC and pulsating DC? Pure DC means it is constant throughout the time, and here it is pulsating in nature or ripple in the nature, wave like we are getting. Though it is positive direction, but it is not constant. So this pulsating nature is due to some AC component in my DC, or I can say AC plus DC. That means inside that some AC component is still there. We are not removing all the AC component or not converting this AC to pure DC. Some AC component is still there. So how much AC component is present in my pulsating DC, that gives the idea of ripple factor. Ripple factor. Okay. Ripple factor means how much AC component is there in my output DC, that given by the ripple factor. If ripple factor is more, then it is not good. That means AC component is more. My requirement is DC. As much as less AC I will find, that is better for my requirement. So if ripple factor is more, then that is not good. If ripple factor is less, then that is good. So that the AC nature or AC component in my required filtering output is less. Understood? In detail, we'll discuss this one. Why these ripples are added and how you can remove this. We will also discuss. So first is efficiency, which is denoted by eta, and second one is ripple factor, which is denoted by gamma. Next one is PIV. So already we have discussed what is PIV, peak inverse voltage of a diode. So if you relate that thing to a circuit also, you can find out of different rectifier circuit whose PIV is more, so that we can operate in worst condition the circuit in the reverse bias condition, okay, without damaging the circuit. So once we have this preliminary idea, then we'll go into calculation of this efficiency ripple factor of this half-wave rectifier circuit. So how to define this rectifier efficiency? You can see efficiency. The efficiency of rectifier is defined as the ratio of DC output power, that is PDC, to AC input power, PAC or PI, and is denoted by eta and expressed in percentage. So eta is equals to output DC power by input AC power, or PDC by PI into 100. Okay, so eta equals to PDC by PAC into 100%. So rectifier circuit, if you observe, just now I have seen, we are giving input as AC and we are getting output as DC. So output is your DC power, input is your AC power. So we will take ratio and multiply with 100 to get the percentage. So that is the efficiency. Okay, clear up to this?
Yes, sir.
Now if we understood up to now, then we'll calculate PDC first, then we'll calculate PAC, then we'll take the ratio and find what is the efficiency. So PDC power, we can write current into voltage, or current square into resistance, or voltage square by resistance. P equals to V into I, or I square R, or V square by R. Anything you can take. So I am taking here all the whatever you will take, the answer will be same. So I am taking here IDC square divided, sorry, I'll take current na into resistance RL. Okay, that means across this resistance how much current will flow or DC current will flow, that multiplied by RL will get the DC power. Okay, so let me draw one clear picture here. Omega T, Vi, this is your Vm, 0, pi, 2 pi, 3 pi, 4 pi. So time period is T equals to 2 pi here. Then at the output, zero, Vm, pi, then pi to 2 pi is 0, again up to 3 pi, here up to 4 pi is 0. So if I represent a voltage or input voltage, then what I'll write? Vm sine omega t or Vm sine 2 pi ft. Okay, and this is your VL or V out. You can also take current signal here. If I take current, this will be II and this will be IL. So here I can also take I equals to Im sine 2 pi ft. So this will be your Im. So any signal you can take, current signal or voltage signal. Now if I want to find out what is IDC, or we can also tell this one as average current, then what will take? The average of this output signal. Okay, so how to find this one? You know the formula, 1 by t integration of 0 to t function. So here we'll find average like that. So what is my time period? 2 pi 0 to 2 pi IL d omega t. I am directly taking omega t as a function. So what is IL? You see here, this is my IL. So IL wave, you can write from here to here. That means 0 to pi, it is changing like sine wave, and pi to 2 pi, it is 0. So I can say IL is equals to Im sine omega t for 0 to pi. Or you take omega t here. I have taken here omega t. So whenever omega t is 0 to pi, IL is equals to Im sine omega t. Yes or no? From here to here, it is changing like sine function. Now pi to 2 pi, what is the result? 0.
Constant. Yes, sir.
0.
Yes, sir. 0.
So omega t pi to 2 pi, we are getting 0. So once you know that one, then we can replace this one here. So IL is equals to Im sine omega t and 0 for 0 to pi and for pi to 2 pi. Now replace this one here. IDC equals to 1 by 2 pi. This limit I will break to 0 to pi and pi to 2 pi. So 0 to pi, what do you get? Im sine
omega t
d omega t plus pi to 2 pi, that is 0. Okay, so this will give you 0. So forget about this term. Now consider the first term here. IDC equals to 1 by 2 pi. So let us take Im outside. So Im by 2 pi integration of 0 to pi sine omega t d omega t. What is the integration of sine function? Sine theta?
Minus cos.
Integration of sine theta?
Minus cos.
Yes, sir.
This
Minus
cos
cos.
theta.
Yes,
Then
sir.
put limit Im by 2 pi minus cos omega t 0 to pi. If you put limit, then it will be 1 minus of minus 1. So it will be plus 2. So 2 to cancel, and I'll get IDC equals to Im by 2 pi into 2. So 2 to cancel, finally I'll get Im by pi. Okay, what is written here? IDC or I average equals to Im by pi. If you take voltage, just everything will remain same. Here you can see I can take voltage signal or current signal. I have derived here by taking current signal. You can also take voltage signal. If you take voltage signal, just opposite will get VDC equals to Vm by pi. Okay, you can try this also. Have you understood this one?
Yes, sir.
Yes,
ये
sir.
डेरिवेशन आएगा सर,
हम्म,
डेरिवेशन भी आ सकता है.
हाँ डेरिवेशन भी आ सकता है. लॉन्ग क्वेश्चन में डेरिवेशन आएगा. So what we have seen, PDC equals to IDC square into RL. IDC you have found out, so just replace here. So PDC equals to IDC square into RL. So in place of IDC I am writing here Im by pi whole square into RL, or Vm by pi whole square divided by RL. So we have found out one term, that is PDC is solved. Now we'll go for PAC. So PAC, have you written all these things? Because the derivation is not in the slide. So you write here. Once you write, you inform me. Is it over? For Fourier rectifier, the derivation is almost same. Only small change is required. That is the limit. Okay. For Fourier rectifier, we have signals from 0 to pi as well as pi to 2 pi. So the term what we have taken as 0, there will be a function. So only that change you have to do. So if you know the derivation of half wave rectifier, you can understand for Fourier rectifier also. Have you written? After this one, then you write this one. So only this part, IDC equals to Im by pi, is not given, which is derived like this. Is it over?
Yes, sir.
Okay. Now we'll calculate AC power. So PI or AC, that means input we are giving AC and we are getting output as DC. We have calculated now DC power. Now we'll calculate AC power. So you know, for AC thing we always expressed as RMS voltage or RMS current. Root mean square current or root mean square value. Root mean square value means all the components are squared and taken as root to find the mean. So root mean square value it is called. So AC power or AC input current can be written as I RMS. And if you calculate power, then same formula, I square into R. So here R means, you try to understand here, we have calculated DC here across the load, but AC means we are giving AC from transformer, so entire circuit it will flow. So you can find AC here as well as here. So the total resistance offered by the circuit is calculated in the AC. So here we find one resistance as load resistance, and as we have already seen the internal resistance of diode, that is something here which is termed as RF, or internal resistance of the diode. Okay, so both the things are in series, so you can take the resistance of entire circuit is RL, that is load resistance, plus RF. You can take small r or capital R, no problem. So RF is the diode resistance and RL is the load resistance. Understood? DC is only getting at the output, so we are taken only RL, and AC, the entire circuit, the current is flowing, so that's why we've taken the series combination of diode resistance as well as load resistance. So once you know what is the power, then we can calculate I RMS. Then we will replace here. So I RMS square is equals to 1 by T, that is time period, integration 0 to T, that is 0 to 2 pi IL square into d omega T. So here also we convert the AC signal into load resistance parameter. So load current, so IL square into d omega T, and limit is, or time period is T. So T is 1 by 2 pi here. So 1 by T integration of 0 to T IL square d omega T. So same thing, we will take it here again. IL is 0 to pi, it is varying as Im sin omega T, and pi to 2 pi it is 0. So we can write it here like 1 by 2 pi, 0 to pi and pi to 2 pi. So 0 to pi is Im sin omega T whole square plus pi to 2 pi 0 d omega T. This is your 0. So I'll take out Im square into sin square theta. So Im square I have taken out. So it is 2 pi 0 to pi sin square omega T d omega T. Then how to integrate sin square theta? How to integrate sin square theta? We'll take sin square theta as 1 minus cos 2 theta by 2. Okay. So cos 2 omega T by 2 d omega T. Take this 2 here. So it will be 4 pi 0 to pi 1 minus cos 2 omega T d omega T. Find its integration and tell me what is the answer. Im square by 4 pi, and this integration 0 to pi 1 minus cos 2 omega T d omega T, or 1 minus cos 2 theta d theta 0 to pi. If you integrate and put the limit, what is the final answer? Just tell me what is the answer of this part, this integration part. What answer? Are you calculating or not? Now finding. So this part will get pi, this part will get 0. So finally you will get pi as your answer for this integration if you put the limit. So I RMS will get Im square by 4 pi into pi. So pi cancel. So I'll get here I RMS square equals to Im square by 4. So I RMS equals to Im by 2, which is written here I RMS equals to Im by 2. If you take voltage, you will get V RMS equals to Vm by 2. Okay. Once you calculate V RMS or I RMS, then you can find the AC power by this formula. So if you put it here, then you can see Im square by 4 or Im by 2 whole square into RL plus RF, or Vm by 2 whole square divided by RL plus RF. This is your input power. So if you understand this AC power and DC power clearly, then efficiency you can easily find, because efficiency equals to PDC by PAC into 100%. So we'll replace this value here, this one as AC power, and last we have calculated Im square, Im by pi whole square into RL as DC power. Have you written all these things? Have you written or not?
Yes, sir.
Yes, sir. Okay. So you see here, efficiency eta equals to PDC by PI into 100. What we have found out as PDC? Im by pi whole square into RL, and PAC is Im by 2 whole square into RF plus RL. Okay. So if I write again here, PDC by PAC into 100%. So eta equals to Im square by pi square into RL divided by Im square by 4 into RL plus RF. So this will cancel. Okay. So what I'll get?
RF plus RL into
4 by pi square RL by RL plus RF into 100%. Now if I divide entire term by RL, then what I'll get? RL cancel. Here I'll get divided by RL. So generally, this internal resistance of diode is much smaller than this RL. Okay, RL in kilo ohm and RF is in only maybe some ohm or 10 ohm, like that, in the range of ohm only. So if I take this one, then efficiency is 4 by pi square into 100%. Now tell me what is 4 by pi square value? RF by RL is much less than 1. So we can ignore this value. So eta equals to 4 by pi square into 100. So what is the value here? If you find 4 by pi square, you will get
0.41. Yes, sir.
406.
Sir, approximately 40%.
So that is 40.6%. 40.6%. So this is your maximum efficiency. So as we have discussed from the graph, you can see this entire half cycle is cut. So if entire waveform is 100%, then we are getting less than 50%, that is 40.6. This is the maximum efficiency, and we are considering there is no drop here. That means whatever Vm I am giving here, I am getting Vm, and there is no drop across the diode. If I consider drop across the diode, then this value will reduce. This Vm at the output will reduce, and if this Vm is reduced, then you can see this DC will reduce. This DC will reduce means your efficiency will be less than this value, or I may get less than 40% efficiency. Whether it is good or bad, if efficiency is less, if efficiency is less, in this case we are getting less than 50%, it is good or bad?
Bad, sir.
Right, sir.
Bad. Okay, so this is one parameter we have seen. Now let us look at other parameter, which is called as ripple factor. So ripple factor, just now we have discussed. Ripple factor means the AC component which is present in my output DC. Actually, using rectifier, I want pure DC, but during this conversion, we are not getting pure DC, we are getting pulsating DC in which some AC component is still there. Now I want to find out how much AC component is present in my output DC. So here, if you look at this diagram, so this is your AC and this one is AC plus DC, or you can also say this is as pulsating DC. So how much AC is present in my DC, output DC, that gives the ripple factor. So if you look at the definition, see, the output of rectifier consists of DC component and AC component. That is ripple. Due to AC component, we are getting the ripple. The AC component is undesirable and accounts for pulsating in nature. So smaller the AC component, the more effective or efficient the rectifier. So ripple factor is defined as the ratio of RMS value of AC component, because AC component is defined in terms of RMS value. So how much AC is present in my DC, that can be represented as RMS value of AC component to the DC component of the rectifier output. So I can write this gamma is equals to I AC divided by I DC. This AC is in your output or pulsating DC, AC in pulsating DC, and this is expressed in RMS, and this one is your pulsating DC. This is the DC value. So there is a confusion between input AC and this AC present in my output. So to avoid this confusion, let us take this AC as not IAC. I'll take I dash AC, or I can take I RMS dash by IDC, or V RMS dash by VDC. Why? Look at here. Here I have taken IRMS when I have calculated AC current, AC power. Here also we have taken AC. So both AC are different. One AC is giving as input, and another AC, whatever output you are getting, in that whatever AC is present, that is your ripple factor AC, or creating the rippleness in the output waveform. So to different both these things, we have taken IRMS dash, which is present in my pulsating output DC. Is it understood? Why the name is different, IRMS and IDC, IRMS dash. IRMS means that is input AC, IRMS dash means the AC component present in my pulsating DC or output DC. Now, gamma will find out, that means IRMS dash divided by IDC. So how will find? Let us assume this output current, this one we can take as DC as well as AC. So if I take DC, then this is pulsating DC. If I assume AC, in which AC and DC both are present. So assuming AC, let us try to find out. So if I assume this is AC and find out the RMS value, then DC component value square plus the AC component value square to the root. Mean we are not taking because this is a larger quantity. So mean means divided by 2. So that value will almost same. So we take square of both component, that is AC component and DC component, and square it. What is my requirement? I require this AC divided by IDC, this one. So that's why I'll just rearrange that one. So IRMS is equals to IDC plus, in terms of this AC, I'll write IRMS dash square. Okay. Then I'll take this IRMS outside, so that I'll get IRMS square minus IDC square root over. And what is my requirement? My requirement is IRMS, this one, IRMS dash divided by IDC. So I'll divide entire equation with IDC. Okay, so divided by IDC divided by IDC. So what will get? IRMS divided by IDC, that is gamma equals to square root of IRMS by IDC whole square minus 1. Okay, so this is for AC, this is for DC, and this is my requirement. So this is the generalized formula. You remember, wherever we take for half wave or full wave, you can use this one. IRMS, IDC we have already found out. Like here you can see, this is my IRMS and this is my IDC, and you just put all these value and will get this result. So gamma equals to IRMS dash divided by IDC. So if you consider half wave rectifier, we have found out IRMS is Im by 2 and IDC is Im by pi. So if I replace in this formula, then I'll get Im by 2 divided by Im by pi whole square minus 1 square root. So if you find all this value, Im cancel, so it will be giving you 1.21. So 1.21 means the AC component divided by DC component, or ratio of AC to DC. in my output DC. So what conclusion we'll get here? AC component is more, or gamma equals to I RMS dash by IDC is equals to 1.21. So numerator divided by denominator, we are getting more than 1. So AC component is more or DC component is more. What is the conclusion?
AC is more.
AC is more. Okay, so that's why we are getting the pulsating nature. You can assume this. So this is due to this AC part. Okay, so two things we have observed here. One is efficiency is very less, that is less than 50%, and the AC component we require DC, but in my DC ultimately I am getting more AC. Okay, so both the case it is negative point or demerit. So generally we avoid this half-wave rectifier circuit. But what is the solution? So we have observed here, due to this half cycle is cutting, we are getting less than 50% efficiency. If I able to make this half portion to upside like this, then it may possible to increase the efficiency. Yes or no? This negative half cycle, what is here, I'll just change to upside. Then you can see the efficiency now it will increase, as well as the ripple. Ripple means you see this top to bottom, the change is very high. Now it is changing, or smoothness of the curve is little bit improved. Okay, so this is one solution. We can, if anyway I can able to get both the half cycle in positive direction, then my efficiency will increase as well as the rippleness will decrease. So to consider that, the full wave rectifier are thought, and here we will discuss two type of full wave rectifier. So first one is center tap full wave rectifier circuit. Then we will discuss bridge type full wave rectifier circuit. So you can see here, this is the center tap transform rectifier circuit. So before that, let us see the center tap transformer. So generally the transformer is like this. We have seen. Okay, so this is your primary side, this is your secondary side. So number of winding depend upon that, it is step down. Now if you observe this one, what is the difference? From the center it is tapped. Okay, the secondary winding is tapped from the center. Understood? That's why it is called as center tap. Center, from the center it is tapped. So if you take this case, then we'll get two voltage here. This is one voltage, this is another voltage. Okay, this is V1, this is V2. Suppose I'll take here 10:1 ratio and here 240 volt. Then if I not take center tap, what is my voltage? In the secondary winding is plus minus. So what is my voltage here? I'm giving 240 volt at the primary side. Number of turn is 10:1. So what is my output voltage? You forgot, you have studied this one in +2 level.
So 24 volt.
24. Okay, N2 by N1 into 240, that is 24 volt. Now if you take some winding at the center, then this will be plus, this will be minus previously. So to make this upper portion another voltage, this will be make negative and this will be positive. So that we get 2 volt here. And this 12 voltage, 24 volt will be divided equally to top portion and bottom portion. So I'll get here 12 volt, here also 12 volt. Okay. So whatever voltage I'll get at the secondary winding, that is divided by 2 part, V1 and V2, or 12 volt, 12 volt. So that's why this transformer is called a center tap transformer, and this transformer is used in this circuit. So it is called as center tap full wave rectifier circuit. So how this circuit is made? First you have to take a center tap transformer, and top side you connect one voltage, bottom side you connect top side you connect a diode, here, and bottom side another diode. Then you join these two, in between that you put resistance, load resistor. So this is the circuit. This is D1, this is D2, this is a transformer, and AC is given here. Okay. So in this case the efficiency will improve and ripple factor also improve. We will discuss in detail next class the operation, and also we will move to the bridge type rectifier and what is the difference between that and efficiency and ripple factor calculation. Up to now, any doubt from today's class? This is very important because the problem will get related to this rectifier, one compulsory problem. You may find derivation also in the long question. So I'll upload this one. You just go through that. If you have any doubt, you can ask me in the next class. We'll continue from here.
Sir?
Yes?
Sir, in the half-wave rectifier, while calculating IRMS, why didn't we taken the mean?
RMS, AC current is always expressed in terms of RMS, not average.
Yes, sir.
DC is expressed in the terms of average. Okay, but RMS means it is AC. So because it is not constant throughout the time period, so we take RMS value. That's why here it is taken as RMS current.
But we have written the formula IRMS equal to root over of ID square plus I bar RMS square.
Where
It should be divided by 2.
That's what I told you, na. If you divide by 2, then it is mean. Okay.
Yeah.
And if you consider this case, because it is like a range of value, so if you divide by 2, then also it is approximately same value. So that here in this formula it is neglected. It's not like that it is not there. It is there, but it is not written. Okay.
Okay, sir. Okay, sir. Thank you.
Because otherwise the value will be not accurate. So we are just calculating the thing. That's why it is qualitative, not quantitative.
Okay, sir.
While explaining also I told you. Just a minute, I will take the attendance. Don't leave. This Monday timing is fixed, right? So everyone should join at 3 p.m. next class.
Yes, sir.
So I'll also change in the timetable, my timetable. Okay, so I have taken the attendance. Now you can leave. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you, sir.